Hello and welcome to the Baller Analyst, the official YouTube channel of IndiaBaller.com. In this category of video where I am discussing about the boiler tube failure, the critical analysis of it and how to prevent it. In the first video, I have promised that I am going to share some typical tube failure problems, how to analyze those issues and how to prevent, primarily how to prevent those issues, right? Uh, In this particular section, I am going to discuss about one typical problem that is called hydrogen embrittlement, which is a very, I would say, vigorous failure, right? Leads to a very damaging condition in the boiler system. And as I have indicated that how to go about it, so we need to understand that what causes it primarily, right? Then try to understand whether those kind of conditions are there in our system or not, and then try to change that so that we can prevent any such failure. It might not be that we start this activity after the failure. If we see those conditions, it should give us an indication that yes, this kind of failure is possible and we should try to prevent it right from the very onset of it. Right now, I'm going to discuss here first of all how the hydrogen embrittlement occurs in the system, that is the damage mechanism. Then I'm going to discuss about the prevention of it. What are the ways to prevent it, and the precautionary measures that are required to be taken. And then in the second part of this video, I'm going to discuss about a case study which I have experienced in my lifetime, right? And that is going to show you exactly how to analyze the problem, how to reach to a root cause, how to see which are the system conditions that is leading to this problem, and then based on that you can take the precautionary measures, right? So beginning with the damage mechanism, that is how the hydrogen embrittlement occurs in your system. Actually, the hydrogen embrittlement is a problem which you can call a secondary problem. Secondary problem is there are some primary cause of failure issue. It may lead to a failure or may lead to a damage mechanism. I told you the damage mechanism doesn't necessarily mean that there will be a failure. But this damage mechanism finally leads to the hydrogen embrittlement problem. So that's why I'm calling it as a secondary problem, secondary mechanism. So it's basically a combination of two things. First, there will be corrosion, right? So a particular corrosion, sets of corrosion mechanism may lead to a condition that is called embrittlement of the component metallurgy, right? In our case, we are talking about the water wall tubes because hydrogen embrittlement is a typical problem of water wall tubes. So in water wall, it's basically carbon steel. So we are talking about the carbon steel metallurgy having a situation when it becomes brittle, right? And if in the system there is a condition of overheating, then the combination of this corrosion mechanism and overheating is going to lead to a problem that is called hydrogen embrittlement problem. Okay, so first let us talk about the corrosion mechanism. There are two types of corrosion mechanism that may lead to the embrittling condition of the carbon steel. First is called the caustic gouging problem, which occurs at a very high pH where free caustic prevails in the boiler water. This free caustic is going to first attack the magnetite, remove it, and sodium ferrite and sodium ferrite will be the result. And then it is going to attack the parent metal, and there will be a gouging type of metal loss. So that's why it's called gouging corrosion. Now, first of all, when free caustic would be there, caustic NaOH is, if you dose caustic, that doesn't mean it will be present in the system as free caustic. It's a misunderstanding of many that we cannot dose caustic, it will lead to a free caustic. No, free caustic occurs at a very high pH. Now this very high pH, where it will occur? Then in the water wall, there can be conditions, there can be situations or locations where the pH is not controlled. I think you all know that the boiler water pH is maintained in the range of around 9.4, 9.5, 9.6, right? But there are locations. For example, if there is a porous deposit, below the porous deposit, this water will become steam and the concentration may increase. And depending upon the ionic balance in there, right, how much sodium and phosphate is there, the pH can either, because of concentration increasing mechanism, it can go either very high or it can go very low. And in fact, if it goes high at a pH of around 11, 11.5, 12, then the free caustic will occur in the system and then the attack will come. So we are talking about water walls, below film boiling, below a porous deposit. Film boiling I have already explained in one of the videos I have shared in under the analytical approach in boiler O&M practices, right? So departure from nucleate boiling, film boiling, the stratification of steam over the surface of the tube. Below this film boiling, we might see the concentration increasing mechanism and therefore formation of free caustic. Okay. Now, there is another corrosion mechanism that may lead to this embrittling problem, and that is the acidic chloride corrosion. Again, the location, water walls, below a porous deposit, below a film boiling, where there is a concentration increasing mechanism available. And if the concentration increasing mechanism leads to a very low pH because of the ionic imbalance, right, you might find that the acidic chloride, if there is a chloride present in the boiler water at that time, the acidic chloride lead to acidic corrosion in the system, right? Now, where chloride will come? Now, chloride can come from condenser leakage. It can come, in the worst case, from the when we treat the water, the demyelination process. So the regeneration, we use the hydrochloric acid. So if the regeneration chemicals are not properly rinsed, there can be leftover HCl that can come to the system, which is a absolute failure of the treatment, right? But suppose chloride is there and the pH goes very low, then also there would be a corrosion. In this case, the hydrochloric acid formed due to the low pH condition will first attack the magnetite, then it is going to attack the parent metal. And then you see, in both the cases, there is a generation of atomic hydrogen. See, from the caustic corrosion also I am getting atomic hydrogen. From the chloride corrosion also I am getting the atomic hydrogen. Now this atomic hydrogen, being the almost the smallest thing in this world, right? It can go anywhere. So on the metal, when it forms, it can go inside the metal, inside the carbon steel. And then what it can do is it can leach the carbon from the carbon steel and become methane. We call it decarbonization, and it weakens the tube. Wow! Because what makes steel steel? You know the difference between iron and steel. Iron is a very strong metallurgy, but it does not have the toughness. It does not have the ductility. That is given to it by adding carbon to iron, and that carbon forms iron carbide Fe3C. It remains within the grain boundaries and acts as a cementite and increase the toughness of the metal. So carbon steel occurs, iron becomes steel. Now from the steel, the carbon is taken out, it goes back to iron condition, so it becomes brittle, right? Now comes the role of the overheating. So this is the brittling mechanism. Both this corrosion mechanism ultimately leading to the embrittlement of the component. And then if there is an overheating condition present in the system, overheating can occur because of delayed combustion. It can be because of flame impingement condition. So basically, combustion disturbance may lead to overheating condition in a system. In a corner fired boiler, the flame ball, which is supposed to be located centrally, may shift to one side of the water wall and thus increasing the heat flux to that part of the wall, right? And when the overheating is there, you see this hydrogen is taking the carbon and forming methane, which is a gas. And these are forming in the grain boundaries, which is the weakest part of this metal. And in the grain boundaries, this methane gas, if it gets heat, right, then it grows in volume and then it ruptures and forms a number of small micro cracks within the grain boundaries. So it's basically an intergranular cracks. See, the microstructure of a hydrogen embrittlement component failure is very, very clear. It does not require an expert metallurgist to understand. When they see the microstructure, you will see small micro cracks forming, number of micro cracks forming. That is a clear indication is a hydrogen embrittlement problem, right? So the best way to check for hydrogen embrittlement, of course, the appearance of the failure itself is very indicative, but to check the microstructure is a very clear indication that what is hydrogen embrittlement or whether it has happened or not. There is another test. It's called ASTM A370 flattening test. In flattening test, if you flatten a component which is under hydrogen embrittlement problem, because it is brittle, they will form a number of cracks both at inside and the outside surface of the tube, right? So when you flatten the tube, it will give the indication that it is an embrittled component. So the overheating part is necessary. Embrittlement has occurred because of these two corrosion mechanism and the formation of hydrogen. But along with that, a combination of overheating ultimately leads to this problem, because when these cracks join, right, they can lead to a very, very big opening in the tube like this, the one which you can see in the screen, right? Uh, and if you see, there is no thinning of the component, right? It's basically a thickly fractured, and the thickly fractured lip, if you see, it will look brittle, right? So window type of opening, very typical of hydrogen embrittlement. If you see the cracked lip, it will look like brittle, right? So you can understand that this component is not behaving like steel. It's a brittle component. So now let us say that we understand, okay, this is the failure, how to prevent it. What are the conditions that was leading to it? So we have seen the location is water wall, where there is a departure from nucleate boiling, where there is a deposit, right? So if the departure from nucleate boiling and film boiling is leading to the concentration increasing mechanism and the corrosion mechanism, so the first precautionary measure, if you want to take, it has to be the avoid the conditions which I have discussed in that video of circulation. Avoid the conditions which might lead to the departure from nucleate boiling, DNB, and subsequent film boiling in the system, right? Avoid all those conditions. I'm not going into the detail here in this video. I've already shared it with you. And suppose you find an indication of lots of deposits that have taken place in the boiler system, right? It can be found out during one of the failures. If you go for a for this looking inside the component and find some deposits, right? And you see that it gives you an indication that the boiler is becoming dirty. And particularly if this deposits analysis shows that there is some conductive metallurgy like copper or brass getting deposited over there. See, these are highly conductive and it creates a strong galvanic sail. And wherever there is a galvanic sail, there is a possibility of corrosion and subsequent deposits. These deposits will again lead to further problem of under deposit boiling, weak boiling that is called, and further corrosion. So if I find that number of deposits are taking place, the boiler is getting dirty. So the next precautionary measure should be for a chemical cleaning and getting the boiler clean. If the number of deposits are more, if I see, right? Now the third thing is that suppose I take care of the location, then I need to take care of the caustic corrosion mechanism and the chloride corrosion mechanism. In caustic corrosion mechanism, what I need to do is I need to have a proper balance of pH and phosphate in the system. The pH should be in the desired range, the phosphate should be in the desired range. When I talk about pH, sometimes in some boilers I have found the pH is going as high as 9.7, 9.8. That is a risky pH for us. For a high pressure boiler, 9.7, 9.8, though it is within the limit. Because if you see the limit, it will be around 9.2 to 9.8 in case of a 120 KSC boiler. In case of a 150 plus KSC boiler, it will be around 9.2 to 9.6. Now the thing is that we have to limit the pH well within that, right? So 9.4 to 9.5, that is what I suggest. We should not get beyond that. So far as phosphate is concerned, there are limiting phosphate given for various pressure system, right? For a pressure system, again 100 to 120 kSc, you will find a residual phosphate requirement is around 6 to 8 ppm. So if you maintain around 6 to 8 ppm, yeah, the range would be given a little more, perhaps 5 to 10, something like that. But if you can maintain a phosphate around 6 to 8 for a pressure like that, it's good enough, right? Again, various conditions, sometimes, it's something I can share with you, that if suppose I find that there is an indication of phosphate going with the steam carry on, it's a natural tendency immediately reduce the phosphate in the boil water. That is very damaging. First of all, we need to understand why the phosphate is going with the steam and stop that particular reason, right? Not reducing the phosphate which is basically required in the boiler water to take care of this corrosion. If I get some chance, I might also create a video on the caustic corrosion itself, right? How to control the caustic corrosion, what causes the caustic corrosion. But for the time being, let us say the pH and phosphate has to be maintained properly, right? So far as the chloride corrosion is concerned, chloride corrosion is because of chloride in the system, and the most likely place of this chloride to come from is the condenser leakage. So we have to critically monitor the condenser leakage, the hot well condition, right? Now, usually, if you check the boiler water chloride from time to time, right, it gives you an indication whenever there is a condenser leakage. Unfortunately, we do not do that. In most of the system, the boiler water chloride is checked only after we have a doubt over the condenser leakage. So I would suggest that why don't we do a critical monitoring of the hot well? This can be done by either a degassed cationic conductivity measurement, or better even, if you check the microsodium with a microsodium analyzer in the hot well. That is a very, very sure way to find out whenever there is even the smallest condenser leakage will be seen by this way. Why? Because a microsodium analyzer can detect a sodium as low as 0.02 ppb, right? So whenever there is a condenser leakage, you will immediately catch hold of it. So these are the two things we have to take care. And whenever you find the condenser leakage, you have to take the precaution, right? Immediately you have to go for the blowdown, find the source, stop the source, or go for a shutdown in the worst cases. Chloride is not acceptable in the system. Okay? And taking care of this caustic and chloride, now let us say that I have to take care of the overheating condition, because the corrosion and overheating both are causing this problem. So for this, you have to go for a combustion tuning, right? First of all, you need to find out whether there is an indication of overheating. You need to check whether your combustion is balanced or not. If it is not, you have to take care of that, right? In my case study, I am going to discuss how this has happened, how I have identified, and what kind of precautionary measure we have taken to take care of that. Okay. And lastly, if you have already had a failure which is seen as a hydrogen embrittlement failure because of either the testing or the look, then it is always advised that when a hydrogen embrittlement occurs in one component, the adjacent tubes are also liable or likely to have the similar problem, right? So go for a checking whether hydrogen embrittlement cracks, micro cracks are seen in there. It may not have led to a failure, but in long run, if the overheating condition persists, then it may lead to a failure. So go for a test called AUBT. That is a basically advanced ultrasonic back cluster test mechanism, which is going to identify whether the micro cracks are there on the components. And when you identify, replace the tubes to prevent subsequent further failure, right? So these are the things you should take as a precautionary measure right before the failure occurs, because whenever such conditions are there in the system, it may lead to a failure like a hydrogen embrittlement failure in your system. Okay, so in my next video I am going to share a case study which will be there, which is going to tell you exactly uh, what are the causes in a system possibly there that can lead to a failure like hydrogen embrittlement, and what are the precautionary measure or what are the correction I have taken to prevent that, which was I can share with you, which was pretty successful. That problem was controlled in the long run, right? So with that, I would say goodbye to you. Please subscribe to the channel to get further notification whenever I put up the next video with the case study part 2 or any other videos. You will get the notification if you subscribe to the channel and click on the notification bell also, right? So with that, thank you very much and bye-bye.